All right, so let's start off where we left off yesterday. Cool guy Mohammed, who doesn't even have his notes out, nor Sam. That's his new handle on Fork Knife. It's cool guy Mohammed 27. Um. So yesterday I was kind of like stuck where I was trying to understand what this question at the end was alluding to, but I just kind of gave up on that, and I decided to kind of frame my own question, which I think is more important, which is, you know, trying to determine whether certain events are dependent or independent. So I'm gonna draw you back to this slide right here, right? And they gave you a couple tests that you can use to see if two events are independent or not. If two events are independent, you already know that you can calculate the compound probability by just multiplying the two simple probabilities. That one we knew already. But these two we hadn't really had a chance to use yet. And by the way, this was a typo. This one here should have been a B. And what this says is, all right, if two events are independent, their conditional probability, which is what these two are, okay, the event of the probability of one happening on the condition that the other one has already happened, should be the same. It should be equal to whatever was the first event listed. Notice how this says probability of A. There's probability of A. This is probability of B. Probability of B. Even though it's the first event listed, it's actually the second event that happens sequentially. Okay, the probability of event A on the condition that B has already happened. The probability of event B on the condition that A has already happened. Those should be equal. So when we come back to this one, now I can ask you, I'll ask you my own questions. For instance, are being right-handed and being male independent or dependent? Well, if that were the case, notice how here right-handed is listed first. So if being right-handed and being male are independent of each other, this should equal that. Are they equal to each other? It's really, really close. If you look at it, 0.86, 0.8696, it's really, really close. And being that, you know, nothing in life is absolute, you could even make the argument that they're independent because they're so close together, but technically it's not. And you can tell by when you round. This one rounds to 86%, that one rounds to 87%. Okay? If I were to ask you, hey, are being right-handed and being female independent or dependent? Well, if they were independent, then this probability should be equal to whichever one was listed first, which was being right-handed. Are those two equal to each other? Again, really, really close. You know, 85% rounded to 86%, really, really close. So, I mean, somebody could make the argument that it's within a margin of error. It's close enough where they would be independent, but by the letter of the law, they're not. Okay? How about here being left-handed? Okay? In order for the being left-handed and being male to be independent, then this would have to be equal to just the simple probability of whichever one you list first. Are those two equal to each other? No. But they're really close, though. They're really, really close. Same thing with being left-handed and being female. It's not the same thing. So what we can say from what it looks like from the data is that there's a very slight dependency. And I think that's why this slide goes on the end to tell you that a fun fact, that if you're male, you're slightly more likely to be left-handed than females are. There's a little bit of a dependency. If you're male, there's a slight chance that you might be left-handed more. I didn't write that, so I don't know. I cannot authenticate that data, but yeah, you know that people used to think that if you were left-handed, it's because you were possessed by the devil.
What? I'm surprised.
Yeah. Yeah. Well, we're not gonna go there, but that's another fun fact. They used to force left-handed people to try to learn to write with their right hand. Yeah. Ambidextrous. All right, so here we go. Find the probability of now dependent events. There are 21 more. Hey, look, marbles. I'm telling you, man, marbles are, you see marbles all the time with and probability. 7 are blue, 7 are red, and 7 I can't read that. 7 are green. Okay. So red, blue, and green. Here's the key word though. Not replaced. So you are removing them, but not replacing them. So what is the probability of drawing a red marble and then a blue marble? Okay, let's start off with the red. How many at the very first draw? How many are red? 7. Out of how many in total? 21. Times, because it's and times. I'm gonna start using the X just because for some weird reason probability they use an X a lot for multiplication. When it comes, see, you can't pick a red and the blue if you haven't already picked the red. So we have to assume that the first event did occur, and now when we move on to the second event with the blue, how many blues would there be? There would still be 7 blues if the first one occurred, but how many total would there be if I didn't put it back? There would only be 20. So the better thing, and hopefully you know how to reduce a fraction, is to try to reduce before you multiply. When we do OR probability, I tell you this because we add, you have a common denominator. But I don't see anything else now in common, so 1 times 7 is 7. We get 7 over 60. Let's show you all the forms, just so you get used to, again, decimals and fractions. Decimals and percents. 7 divided by 60. I'm getting 0.1167 approximately. 0.1167, which is around how many percents? Around 12%. How about drawing a red marble, then a blue marble, and then a green marble? Yeah. Well, here, now look, we can see. Yeah, you should be able to do this. Since we already calculated the red and then a blue, we know that that came out to 7 over 60. We can just take up there and say, all right, now assuming those two happened already, by the time it came time to pick a green marble, how many greens would there be? There would still be 7. But how many would be left inside the bag? Now they would be down to 19. Wow, you answered that a lot quicker than I thought you would. Good. So 7 times 7 is 49. 60 times 19 is 1140. So 49 over 1140. I couldn't reduce anything before, so you shouldn't be able to reduce anything afterwards. But you can make it into a decimal. I'm getting approximately 30, which is around 4%. Now, also, here's another fun fact. If I were to ask you to just go in the bag and pick 3 marbles, because you can, without looking, you can feel if you have 3 marbles in your hand. If you pick them out at the same time, the probability counts the same way as this. Because at the end, you're going to be holding the 3 marbles in your hand at the same time. The same way if I were to go 1, 1, and 1, the fact that I ended up with 3 in my hand and 19 left inside the bag, that would be the same probability of getting them 1 at a time, and it would be the same as getting all 3 at a time. So you have about a 4% chance in this bag that you just randomly go in there and get red, blue, and green. 4%, yeah. So to put that into context and make a little bit more sense, you would theoretically that put them back. Pick 3 marbles, put them back. Pick 3 marbles, put them back. And if you do it approximately 25 times, because 25 times 4 is 100, you should be able to pick red, blue, and green ones. Hash brown facts. So you can go do that over the weekend when you're bored. Do you have marbles at home? Oh man, do you ever play that? What's the name of that game? With the marbles. Oh man, Mancala. That's a game. Yeah. It's because me and Lana go way back. Mancala is like a game of marbles, and it's like a tray, and then you have to pick them up and you drop them off and stuff like that, and then and you keep on going until you end up in like a little well that's empty, and then at the end you have to see who has marbles. Well, two ways of playing. You can play, see who ends up with the most marbles on their side, or you can end up to see who ends on their side, like who ends up first. There's two ways of playing it, but that's a good game. All right. Ooh, of drawing a red marble or a blue marble and then a green marble. So, ooh, look at this combo review time. Or an and. Okay. So now the way I'm reading this is that how many total events are there? Two. That the first event is going to be red or blue. Okay. And then we're going to go with the green. So I'm reading this as two events. Okay. So for the first, how many red or blues are there? If it's one or the other. No. Or 14. There's 14 that are either red or blue. 14 out of 21 times, assuming that they said no replacement. Okay, now when you go back for the green, how many greens are there? 7 out of how many? No. 20. 14 out of 21. This reduces to 2 out of 3, and I can also be gangsta and then reduce this 2 to a 1 and then a 10. I'm just trying to keep the number smaller. Do you guys remember how to reduce fractions? What's the biggest number I can divide 14 and 21 by? 7. If I divide them each by 7, the 14 becomes a 2, the 21 becomes a 3. But now I still have this 2 on top and a 20 on the bottom. What's the biggest number I can divide 2 and 20 by? No, by 2. If I divide each one by 2, 2 becomes 1, 20 becomes 10. Now there's nothing else I can do here, and the numbers I'm left with on top are 1 and 7, which gives me 7, and the numbers on the bottom I'm left with are 3 and 10, which gives me 30. I have a 7 out of 30 chance, which to put it in decimals gives me 0.233 repeated, so that's about 0.2333, which is also around 23%. So this one you should probably have to attempt about 4 times. If you do 4 sets of it where you pick out 2 marbles and pick out 2 marbles and pick out 2 marbles and pick out 2 marbles, one of those times you should end up with a green, and then the second one could be either red or blue. Of drawing a red marble given that the first marble drawn was already red. Okay? So how many events are you calculating here? Just one, because all they want to know is drawing that second red marble, because they have already given, we're already assuming that the first one was red. So that second marble, how many reds would be left? If the first one, if we already know it was red, how many reds would be left in? 6 out of how many in total? Good. That reduces by what? By 2. So this becomes a 3, this becomes a 10. 3 out of 10, which we know is 0.3, and that is exactly 30%. So if you basically go in with your eyes open, take out a red already, and then go back in for a red, you now have a 30% chance of getting a red. Questions there? All right. Depending on how fast, if we can finish all this today, then we do the Kahoot tomorrow. If we can't finish all this, then the Kahoot gets pushed back to Thursday. Either one is fine. Tomorrow is Wednesday. Today's Tuesday. I know, yeah. Yesterday kind of felt like you guys weren't here at all, so yes, I could see why you would feel it's Monday. Given a standard deck of 52 cards, which consists of 4 queens, 3 cards, what? 3 cards are dealt without, man, this thing is cut off, without replacement, okay? All right, so that's the key word there. We are not replacing, so we're keeping things out, and we're dealing 3 cards. What is the probability that all 3 cards are queens? Since we're not putting them back, for the first queen, how many queens would there be? Didn't we? I feel like we already did this one, but wasn't it aces? Well, with aces or something, or kings? I feel like we did this one. No, maybe it was up here before the spinner. 3 cards are dealt. All 3 cards are kings. All right. So then I'm gonna skip that one. We did that one already. It came out to 0.2%. I don't want to repeat the same thing. If the first card is a queen, what's the probability? All right. So this one seems new. Assuming that the first card is a queen, so we've already taken out a queen. What is the probability that the second card will not be a queen? All right, that's a good one. So if we take out a queen now, okay, how many total cards are left? There's 51, right? But how many of those 51 left are queens? Because I've already taken a queen out. 3. So then how many are not queens? What's the complement? See, like, look, there's 2 ways. Here, perfect. Let's use. We haven't used complementary logic too much yet. So let's do this. When something is not, okay, that's the complement. Remember that little apostrophe symbol that we saw before the break? The complement of a set? Okay, so when something is certain to occur, what is that as a decimal? Or better yet, what is it as a percent? If an event is certain to occur, what is the percent? 100. And how do you write 100 as a decimal, or 100% as a decimal? 1. It's not a decimal. It's just 1. It's 1 whole. Okay. So what I could do is say, all right, well, let's calculate what a queen would be. Well, there's 3 queens out of 51, but then you can just do 1 minus that, and that would give you whatever's left over. Yes. Say that again? Yeah, correct. That would be the other way of doing it. It's just saying, well, hey, there's 48 cards left. It's 48 out of 51. Yes, that is perfectly fine. But you can also do the 1 whole, and what everything is left minus the 3 queens out of 51. That would also work. It's going to give you the same thing. This can be reduced by 3. So this becomes 16 over 17. If you reduce it by 3. So we get about 9.9412, which is approximately 94%. You have a 94. If you take a queen out, you now have a 94% chance of not getting a queen. Of not sure, because almost everything else that's left is not a queen. There's only 3 queens left. Okay, good. All right, we had a little fun yesterday with number cubes. Okay, this is kind of the same little chart that I showed you, right? Remember we learned yesterday? What's the most common sum you can have when you're rolling 2 dice? Yeah, 7 is the most common outcome. This kind of just shows you, and this actually looks better because you actually see the cubes. 1 is red and 1 is blue, and you can see how the most common sum is still. You can still see it's 7 there. All of those add up to 7. 6 plus 1, 5 plus 2, 4 plus 3. So the 2 number cubes are rolled. 1 is red and 1 is blue. Find the indicated probability that the red cube shows a 1 and that the sum is less than... Oh, God, they're going to make me count each one then. All right. All right. So that the red cube shows a 1 and that the sum is less than 4. Okay. Damn. Well, there's 2 ways to do this. How do we do this? Probably we can do the intersection divided by the. Yeah, I think it's just easier to do it by hand. Since, maybe because you can use the formula, but since they're giving you a table, they probably just want you to count. So let's just do this. So remember, this is an end. We're looking for the intersection. So we only want to look. Let me move this out of the way. We only want to look at the ones that where the red cube shows a 1. Okay, so that can only be here. Right? How many of those are there? How many of those are there? How many do you have that the red cube shows a? Yeah, 6. And by the way, how many are there in total? Yeah, so there's going to be out of 36. We know that there's 6 of those, but out of those 6 only, how many have a sum that is less than 4? No, I'm counting 2. Only 2. Because it says less than. This sum is 4. So I'm only counting 2. So 2 out of 36 is 1 out of 18. 1 divided by 18 is 0.0556, which, as Lana knows, is around 6%. So what's the probability that the blue cube shows a multiple of 3 and the sum is 8? So we're looking for the intersection. All right, between 1, because all the numbers are between 1 and 6. Okay. What are multiples of 3? Well, 3, 8? No, 3, 6, 9. Oh, he said 6. Sorry, it's a mask. Okay. So just 3 and 6. So we're only looking at because multiples are like counting by that number. 3, 6, 9, 12. And the only numbers here, Angel, are 3 and 6. So where we have the blue cube of the 3, I can almost guarantee you that it's almost a certainty that every single one sitting in this class, assuming you're going to graduate, is going to take stats and probability, or statistical reasoning, what they call it. So, like, this is what you're going to be doing for an entire year. So this would not be the time you want to fall asleep. I actually, in my 7th period, I actually have a kid who's taking it now because his graduation year is supposed to be now. So he's actually taking that at the same time as this. And it actually makes it a whole lot easier for him. So, like, this is probably this whole thing about, oh, when am I ever going to use this in life and stuff? Well, I don't know. I don't know when you're ever going to use it in life, but I can tell you this unit, you're going to use it again before you graduate. So you'd want to, yeah, like more than anything about arcs and chords and all that other stuff that we've done this semester, this is probably the most pertinent to your future. So, well, you got to study everything. You gotta study everything, but I'm just saying this is what you're gonna see more of. The blue cube shows, so we got that part, and now the sum is 8. Out of those 2 circles that I drew, how many add up to 8? Let's see, 5, 6, 7. So we got this one adds up to 8. It's only gonna be 2, and then this one here adds up to 8. Still also 2. So out of the set, there's 2 out of 36, which is, again, 1 out of 18. Oops. 80. 1 out of 18. It's the same thing. Which is approximately 0.556, which is around 6%. Same thing. All right, any questions? Okay. In a certain town, the probability that a person plays sports is 65%. The probability that a person is between, oh yeah, this is okay. I read this one before. The probability that a person plays, I'm going to rewrite this because I had to read it like 5 times the first time I read it. So, sports is 65%. Okay. The probability that they're between ages 12 to 18 is 40%. The probability that a person plays sports and is between the ages of both, okay, so the intersection, let's just say both, just to save space, is 25%. Are the events independent, and how would you know? In order for events to be independent, we talked about it at the very beginning today. There's a couple ways you can check. You can either check what we saw earlier, which is that the conditional probability is equal to the first one. Okay, or if they give you each independent one, each simple probability, which is what they're giving us here, they're letting us know the simple ones. In order to be independent, I should be able to just multiply them and get the intersection. So let's see. That's the one I'm going to use. And we won't do it as percents, we'll do it as decimals. So this is 0.65 times, how do I write 40% as a decimal? Come on, Miranda. Don't phase out on me. How do you write 40% as a decimal? Just 0.4. So if that gives me this, then they're independent. If not, then they're not. 0.65 times 0.4. I'm getting 0.26. Are they independent? Yes or no? Yeah, they are not. Not independent. They're dependent events. Okay. For which set of probabilities would events A and B be independent? So here, I'll let you guys do this one. Okay? Notice how they're giving you each simple probability. They're giving you event A, event B, event A, event B, event A, event B, event A, event B. So if they were independent, what should be true? Not add up. If you multiply each simple one, that would give you the combined one. So go check and see which one of those multiplies to give you the compound probability. I'm doing it in my head, but I think I know the answer. Oh man, it could be two of them. I hate decimals. There's two that it could be. So do you guys have a calculator? Or are you always doing this? Huh? In my head, I'm either getting, I haven't put it in a calculator yet, but I'm getting either B or D. Those are the two I would test. Like I can pretty much assure. Well, I know, even though again decimals are not my favorite, I know this time I know 0.25 times 0.25 doesn't give you 0.5, and I know 0.16 times 0.24 does not give you 0.32. So in my head, I would narrow it down to those two, but then B is wrong. Okay, 0.08 times 0.4. Yeah, that's 0.32. Yeah, and actually, yeah, I should have known that too. 0.8 times 0.4 is not 0.12. Yeah, so it's gonna be 0.3 times 0.15. Yeah, D. 0.3 times 0.15. I haven't heard a peep from anybody at home, so either you're just not listening. Did Yannick ever show up? Yeah, there's the Y there. Yannick, let's do an attendance check. Is Yannick there? All right. I called you yesterday again, and you weren't there. The end. Okay, good. It looks like we are going to finish today. Perfect, so we can do the Kahoot tomorrow. A and B are independent. Okay, they're giving you the probability of each. Find the conditional probability of event A on the condition of event B. Now, before you go crazy using any formulas, that's the key word there. They're independent. So what did we learn earlier today? What if events are independent? Huh? Their conditional probability should be whatever the same is as the first one listed. So what's the answer? No, come on. If the events are independent, they want to know that they're not asking, look, if they were to ask you for the probability of A and B, then we're doing it the same way we did the last time, where you're just multiplying. But they're not asking you for that. They're asking you really only for the probability of A, but on the condition that B has already occurred. And I showed you on the very, very first slide we did, okay? When they're asking you for a conditional probability, if the events are independent, it's going to be just the same as whatever the first one listed is. 0.26, bam, done. Equals 0.26. I might make it a 2-day Kahoot. I might make it, because I remember this Kahoot had a lot of questions. So I might break them down into 2 different days and just do a 2-day, and I'll even give you the points for both days. Is that something you'd be interested in? Alright. That's probably what I'll do then. Assume that the following events are independent. Damn it, there wasn't so much. Alright, so then we're going to have to rely on the Kahoot then for more examples of dependency, because there's not a ton of, most of the stuff was independent. So if we assume they're independent, the probability that a senior goes to college is 0.72. The probability that a high school senior will go to college and live on campus is 0.46. So what is the probability that a high school senior will live on campus given that they will go to, all right, so here, let's write this. So college, let's use notation. Probability of college is how much? Come on, there's the last one. Fight through it. 0.72. Okay, probability. These are actually the type of problems I wanted more of, and there's only one of them. Thought I had more of these. College and live on campus. And let's say campus. Oh, actually no, but they're independent. Let's see, is 0.46. Okay, so yeah, all right. So all they did here is because it's independent. Yeah, this is still not the one I wanted because it's not dependent. But the point is because it's independent, how would you calculate the and probability? Not the conditional probability, but the and. How would you calculate it? Not adding, but just multiplying. So what this is saying is that 0.72 times something gives you 0.46. So how would I figure out what that something is? And that something being just the simple probability of living on campus. Divided, sure. So let's do, and it's 0.46 divided by 0.72. That gives me around 0.64. Okay. But wait, there's more. The question doesn't ask you just for the probability of campus. They want to know, the question is asking you, what is the probability that they will live on campus? Well, they both start with a C. So let's just say campus on the condition that they already go to college. Well, because we know the events are independent, that conditional probability is going to be the same as whatever the first one was. So what ends up being the answer then? Yeah. It ends up being that 0.64 that we just found. We have 15 minutes left in class. Those of you that are, I'm done with the notes. There's still more to practice. I believe it's Khan Academy again this week. If I remember correctly, it should be Khan Academy. I know you've all started. Work on that. I'll make the Kahoot into a 2-day Kahoot. So we'll do Kahoot tomorrow and we'll do Kahoot again on Thursday, just to try to get you exposed to some different types of problems. But I would hope that you would also do that on with the homework. And then Friday will just be a homework day. Well, no, that's the whole point. It's not easy. I want you to work. There's only like 2 or 3 people that have decided to keep on working and stuff, and it's hard to just expose you to problems if it's just me up here on the board. The whole point of the homework is to get you exposed to more problems for you to say, crap, you know what, I don't understand how to do this. You know, Mr. Romero, can you help me? Hey, you have to try to reason and think through things, and that way we don't bomb the test. So, any questions for me before I tune out or sign off? Stay on so I can make sure the attendance is right. The people that are here, you got 15 minutes. Just get on the computer, log in. At least familiarize yourself with what we're doing this week. And then let me check attendance. The people at home can go work on the assignment as well.